So today I want to talk to you about what I call a backstop for inaction. And this is a set of technologies and methods that are discussed a lot right now as the world is confronted with the fact that it's going to be extremely difficult to stay under 2 degrees, right? And so countries, companies, et cetera, are looking for ways to dig our way out of an overshoot of atmospheric CO2. And so I'm going to talk about a couple different topics. The majority is negative emissions. But first I want to define what a carbon offset is. And this is an idea that you hear about a lot. If you read about climate change, you'll know about offsets. Some of you, has anybody purchased offsets themselves to do anything? Ever purchased an offset? You can purchase offsets, for instance, to offset your air travel, for instance, right? And in some places, when you go to fill up your car with gasoline, you can buy an offset. You can buy an offset gasoline, and it costs a little bit more. And so we'll talk about what that means. It generally means an avoided or a negative emission to offset the positive emissions that you've just done or are about to do. Now there are 2 categories of offsets. The first is, and they're linked for I guess historical reasons. First is to reduce non-fossil emissions. That is, the important thing is non-fossil, of CO2 or other greenhouse gases, including methane. So something that isn't a fossil fuel reduction for some reason is called an offset. Okay, it's offsetting fossil fuels. The second is to create a carbon sink, to actually actively create a carbon sink that generates negative CO2 emissions. Okay, so let's start with the first category, which is to reduce non-fossil emissions of CO2 or other greenhouse gases, including methane. The one that is, if you go online and purchase offsets, carbon offsets, you're almost always purchasing, like the first thing you'll see is an avoided deforestation offset. And this is an offset that basically buys the rights to a piece of ground that is usually primary tropical forest. And the payment pays the owner not to chop it down or convert it into something, okay? And so the way to think about this is that in 1 hectare of land, again, that's 100 by 100 meters of land, there's around 200 tons of carbon, not CO2, but carbon, in the living vegetation and about 100 tons of carbon in the soil. And if that's converted into cropland, then you lose about half the soil carbon from plowing up the land and repeatedly exposing the undecomposed organic matter to the air so that it decomposes more rapidly, and you lose almost all the above ground vegetation. And that total loss of carbon converted to CO2 is like 900 tons of CO2 right there, all right? So that's a lot, right? 900 tons of something is like a pretty big boat's worth, right? It's a lot, right? Think about sort of an average yard is a half an acre, or about a quarter of this. So that's like 200 tons in your yard, okay? That's a lot. 200 tons is a couple of, like 4 big semi trucks. All right, now there are specific areas in the world that are the primary focus now for offsets for a very special reason. And in Southeast Asia in particular, there are large areas of peat forest. And peat forest has peat below ground, like peat moss that you buy, undecomposed organic matter that because of special anoxic and waterlogged conditions has accumulated there over eons. And this will have, instead of like 100 tons per hectare below ground, have like 1,300 tons below ground. And if you chop it down, and it's currently being converted to produce palm oils, right, for the US and Western European food markets primarily, but actually worldwide, you lose all of this stuff. So you lose 5,000 tons of CO2 per hectare. That's the emission that it was produced. So if you offset that, it turns out to be incredibly cost effective. All right, so remember the 5,000 tons. Now these are peat forests, and they're being converted into palm oil. This is the area of palm oil covered land. These are millions of hectares, and this goes from 61 to 2006. And you see those are all increasing. Not all of this is Indonesian peat forest, but it's the Indonesian peat forest that I want to talk about. There's about 20 million hectares of this Indonesian peat forest that has 5,000 tons per hectare in it, that cutting it down causes to a net. And the important thing is this: if you're an Indonesian poor person who owns a chunk of primary rainforest and you convert a hectare of it to palm oil, the net present value of that conversion, like the future earnings, discounted, the way that economists do, is about 15 grand. Now, 15 grand is a lot of money to a person like that, right? That buys a different way of life. And if you have several of these hectares, you can set yourself up as a wealthy person. And so the inducement is just extraordinary. But because there's so much carbon in the peat forest, the price to prevent them from doing so is only $3 per ton of CO2. So 3 times 5,000 is 15 grand. So you can get more than the value of the conversion for just $3 a ton for CO2. So if you go online and you ask, now you remember that Mark Fleurbet yesterday was talking about carbon prices of $40 or $100 a ton. And remember the 45Q rule that pays people now to bury CO2 in carbon capture and storage now inside the US, that's $50 a ton. So this is $3 a ton. So why so cheap? Well, it's cheap because there isn't a global carbon market with tea. If there were, nobody would ever convert another hectare of rainforest again, right? Because the price would climb to 20, 30, 40, 50 bucks. But you can get one of these online for $3 right now, simply because it's enough to pay the person, and then you can own it, right? So collectively, people that pay $3 a ton own $15,000 worth. They own a whole hectare, and then there are various levels of sort of legally binding structures that maintain this in perpetuity or not. So there are all kinds of fly-by-night organizations that will sell you a piece of rainforest, and then they put another sign on it, sell it again, sell it again, sell it again, sell it again. And there's rating systems for these. You can find that. You can read all about this online. So there's ways to do this, but that's why offsets are so cheap. This is a recent TNC. TNC means the Nature Conservancy in NGO speak, which is the largest environmental NGO in the world, annual budget over $1 billion, and they buy up land and put it away, and they've become preoccupied by various ways to modify land use so as to offset or reduce carbon emissions. And this is a recent study that was just published this year, and it was sort of 3 years into work, and they conclude that avoided forest conversion would save you about 3 billion metric tons of CO2 annually. If you did so at under $100 a ton and at under $10 a ton, it's 2 billion metric tons of CO2. And the important thing is that this number represents the entire current global deforestation source, which is 9% of global emissions, which are currently at 35 gigatons CO2 per year, right? That's the current global emission. 9% of that is just about that number, all right? So this represents elimination of the entire global deforestation source, and what you should take from this is that you could get half of it at less than $10 a ton. So the message here is one that I think is pretty easy to understand. As we get serious about the carbon problem, the problem will cause deforestation to cease relatively rapidly. That's one of the reasons why, if you track the deforestation source through time, it has been going down steadily. And it's because it's so cost effective to mitigate this first. And from an ethical point of view, it's the first place you want to do it anyway, because not only does it help fix the carbon problem as well as reducing fossil CO2 emissions, it also works directly on the biodiversity problem. So you get a twofer out of it. Okay. Now, so avoided deforestation is a good deal. It has co-benefits for biodiversity, like I just said, and also forest ecosystem services. The forest keeps doing what forest does for local people and wildlife. But it has some concerns, and these concerns are words that if you read the newspaper, you'll read about. One is called additionality. Additionality means if you had paid the money, if you didn't pay the money, would the forest have really been cut down? Okay? So if the forest hadn't been cut down anyway, paying the money so that you think you've displaced emissions, you really didn't displace them. And so your emission is still just an emission, right? So you didn't offset anything if the forest wasn't going to be cut down. And so it's not clear that it's difficult to show additionality. You have to sort of somehow snatch a plot of rainforest from the imminent destruction by some chainsaw wielding person. And that's difficult to show, right? Second, there's permanence. And this is even more vexing. Carbon problem requires that CO2 stay out of the atmosphere essentially forever, right? Because it's so long-lived. And so you have to think about this as a permanent conversion of land about to be deforested imminently to remain forest permanently. What you got?
Yeah, I got it. Just into my email.
There's the version with the teaching objectives at the end, and my assistant sent the wrong one this morning. It's mad annoying. Okay, so I will talk without notes for a little while, or without slides for a little while. Oh, see what I can't know his password. Okay, so the second one is permanence, right? And you need a legally binding structure that does it. So this is really difficult to do. One of the best groups that does it, believe it or not, is the oil company BP. And it's because for years in Europe, they've been giving people the option at the pump to avoid deforestation by paying more for gasoline. And so they've got this group that is like super into regulations and rules. And what, you got it?
Yeah.
Dynamite. And what they do is they basically buy it up, and then they deed it to the government as a national park. All right, and that's the right way to do it. Right? The final one is leakage, and leakage is pretty straightforward. Also, if that land was going to be used from some purpose that has an economic driver, let's suppose the land, instead of going to palm oil, was going to timber. There's still a demand for timber in tropical countries. So if you don't cut this hectare down for timber, do you increase the economic incentives, which causes another hectare to be cut down? So you're really not preserving it. The problem here is you need sort of a global system. So this is all very, very difficult, and there's a huge amount written on additionality, permanence, and leakage. It's a tricky subject. All right. Now, that's it for offsets. I want to talk now, or avoided non-CO2 emissions. I want to talk now about negative emissions. And this is from a UNEP report that was just published. And this is a below 2 degrees C emissions trajectory. These are emissions, gigatons of CO2 per year. This is time up to 2100. And this is actually RCP 2.6, the one we keep talking about. This is some business as usual trajectory. The net emissions are shown here. In brown, this sort of darker brown is other greenhouse gases. This lighter brown is CO2. And this blue thing down here are negative emissions that are supposed to be created. We're supposed to deploy negative emissions technologies. And what they do is these blue emissions offset the brown emissions so that when the height of the brown equals the height of the blue, the net emissions on red here are at 0. You see? Now the point is that this is the most recent IPCC report became preoccupied by this thing And because they couldn't get this trajectory to happen with standard technology in a cost-effective way, they defaulted to these negative emissions. And economic models, which are just blind to choices, chose an enormous amount of it. And then everybody said, is this possibly feasible? Minus 20 gigatons per year of negative emissions. We're going to create things around the surface of the Earth that suck down 20 gigatons of CO2 per annum, more than half our current global emissions. And by 2050, this number gets, or by mid-century, this number gets to about minus 10. Okay? And so what are these negative emissions, and could you possibly do it at this scale? It sounds crazy, like a giant Hoover, you know, that would like suck down that atmospheric CO2 at a rate that's like, you know, that's like, the way to think about the negative emissions, there's a whole bunch of ways to do it, is you can also think about it as an offset. So in this case, this is a little picture that shows what happens when you drill seeds into the soil and put a cover crop on a farmland, rather than plowing them up annually. And the land will start to take up CO2. And if you paid for this process, the combustion of 1 gallon of gasoline plus 10 kilograms of CO2 captured from air and sequestered equals 0 net emissions. There's about 10 kilos of CO2 in a gallon of gas. And so if you did 10 kilos worth of this, you've basically offset the entire gallon of gasoline, right? If this costs $10 a ton, the numbers remember we've been talking about are like $3 a ton, and we were talking about, you know, the Q45 rule, which 45Q rule, which is $50 a ton. $10 adds 7 cents a gallon of gasoline. Easy to remember. $100 a ton of CO2 adds $1 a gallon. So $50 a ton, like the 45Q rule, is 50 cents a gallon on gasoline. $3 a ton, like the rainforest stuff, is 3 cents a gallon. Right? Tiny little number. So what are these negative emissions methods? Well, there's a bunch of them. You can increase the total mass of living and dead wood on the planet. Talk about how to do that. You can increase the amount of soil carbon in cropland and pasture soils. You can grow biomass, burn it in an electricity-producing power plant, capture the CO2 as it comes out of the smokestack, compress it into supercritical CO2, and inject it in a geologic reservoir like the ones that natural gas comes from. Now, that sounds complicated, but the CO2 came out of the air to come into the plants. You're now harvesting it, you're making electricity. The CO2 goes up. That would normally be an emission that canceled the negative emission from the photosynthesis that went into the plant to begin with. But you catch the CO2 and you stuff it in the ground. So the negative emission that built the plant still exists. The positive emission you've stuck in the ground, and so it's a negative emission on the atmosphere, right? There's direct air capture. These are machines that pull CO2 out of the air, put it into supercritical pure CO2 form, and allow you to inject it in the ground. You can actually buy one of these on eBay. There's a Swiss company that makes one, and it works. It's like this big. I want one, right? I don't know what I'm going to do with it, but I want one. and you turn it on, and it sucks CO2 out of the air at a pretty good rate too. And it's expensive, but not expensive if you have a use for the CO2. Like if you run a greenhouse and you want to grow vegetables in the winter, if you run it under enhanced CO2, because plants eat CO2 for a living, you get way more strawberries out of your greenhouse. And so vegetable growers, far from the grid, are willing to pay $1,000 a ton for that CO2 because they more than make up the money on the vegetables. And this machine will put it into your greenhouse for $600 a ton, which is why this company exists. Okay. All right, you can accelerate the mineralization of CO2 into minerals. And this is really interesting and hasn't been explored very much, but it's about to be a big industry, I think. Turns out that some mine tailings are reactive with CO2. Pull it out of the air and turn it into carbonate rocks. And by just managing these mine tailings differently, you can get it to suck CO2 out of the air. It's also conceivable that you could actually mine rocks that have these properties. Brucite is the best possible mineral if you want to look at brucite. You stick brucite out, you crunch it up into powder, and it just pulls an enormous amount of CO2 out of the atmosphere where it's stable for geologic time. You can fertilize the oceans to accept deep sea accelerate deep sea carbon storage. These methods, there's a lot known about how to do these, but the problem is that Greenpeace will bomb your headquarters if you try. Everyone freaks out. You go in here. And you can increase the carbon stored by sediments in coastal land. Turns out coastal lands really accumulate organic carbon in the swampy areas, the coastal marshes, essentially linearly through time. And as the sea level rises, they just keep building it up and up and up and up. And so if you rebuild coastal marshes, you actually can cause the CO2 to come out of the air and into this coastal sediment. Now, I've got, I really want to run out of time. I'll do this a little bit. If you read about negative emissions technologies now, there's a lot written about in papers, in the newspaper. There's a big article on this in the New York Times just last week. And you read all kinds of things. One in particular is ethically, they represent a moral hazard. And they represent a moral hazard because if we can pull CO2 out of the atmosphere, and our technology for doing that is just going to develop, why do we really have to reduce emissions now? Can't we leave it for later generations who are going to be richer and more technologically adept because they'll be able to just pull it back out again? And especially because the climate change lags the atmospheric CO2, they won't really experience 2 degrees of warming for a while, and they'll be able to do this later. So that's the sort of slippery slope of the moral hazard. A lot written about that. And then there's all kinds of stuff written that turns out, and this is the punchline is going to be that all these are false, even though they're written about again and again and again, including the current president of the National Academy of Sciences wrote a big long thing on this, and all these things are false. Okay. One is that negative emissions technologies represent the only way to reduce atmospheric CO2. That without negative emissions technologies, we can't reduce atmospheric CO2. Turns out to be false. And then there's a couple of others that you can read about, but I'm not going to ask you about. There are other reasons why negative emissions technologies are difficult. And all of these turn out to be false. And the reason that they turn out to be false, and the one I want to focus on is the one I just mentioned, is because of the natural sinks. You remember that only less than half of the CO2 that we emit into the atmosphere actually stays in the atmosphere. The rest is absorbed by natural sinks on land and in the oceans. The oceans and land are gaining carbon weight through time, and a lot more than half we emit. Now, this is RCP 2.6. And RCP 2.6, that trajectory we were just looking at, reaches a maximum CO2 concentration in 2050. It's about 442 parts per million. And then it strikes this long, slow slide, all right? And the long, slow slide drops the atmospheric concentration by about 25 ppm by the end of the century. And all the way out here at 2300, we're almost back at 350 ppm. A nice, low, super safe number. So the question is, how did we get back there? And it's widely viewed that we get back there only because of negative emissions technologies. And without them, we couldn't possibly reduce atmospheric CO2 this way. Now, this is a so-called waterfall diagram, and it's by a paper by a climate scientist named Jones in the UK. And it's about specifically that scenario, and so I want to show it to you. So this is the atmospheric concentration in parts per million of CO2 in 2050, 443 parts per million. I said 442, it's 443. And this is the atmospheric concentration in 2010. And in that RCP 2.6 scenario, here's how you get from 443 to 418. Well, first, humanity in this 50 years is going to emit 83 ppm. And then it's going to deploy negative emissions technologies. They're going to suck up 62 ppm. And then the land sink, the natural sink, is going to pull down another 20. And then the ocean sink is going to pull down another 27. And if you take this positive emission, this negative emission, this negative emission, and this negative emission, the atmospheric concentration here drops by about 25 parts per billion, by exactly 25 parts per billion. You see that? You see how that works now? Or is somebody confused by that? Speak up if you're confused. Okay, so this one goes up to concentration. If it were just the fossil, we'd take it up to 510, but then there's this and this and this and this. Now the thing I want you to notice is that the sum of these positive and these negative emissions is still positive. 21 parts per million. Humanity has added to the atmosphere. And even though we added an extra 21 ppm to the atmosphere, the concentration dropped by 25 ppm. And the reason it did is that these sinks are persistent. They keep going, even though the atmospheric concentration is dropping. And even though they overwhelm here the emissions, the positive emissions that humanity did. So in other words, if humanity deployed no negative emissions technologies at all, but just emitted with fossil fuel 21 ppm worth, then we would still get this trajectory, right? We'd still get a big reduction in atmospheric CO2 without any negative emissions being put out into the atmosphere at all. Now, why does this work? And then blah, blah, blah. Okay? Why does this work? It's because disequilibrium dominates. Okay? Now, I want to explain how this works because it's another benefit that the natural, the reason is, this turns out to be because the natural sinks are strong enough that they're able to pull down atmospheric CO2 even as humanity continues emitting, as long as we emit at a reduced rate from where we are now. Why does this work? Well, the ocean looks like this. Remember, there's this drain in the oceans where it drops into the abyss. And the abyss is so thick, it's like a deep river that goes really slowly. And the water spends 1,000 years crawling along the bottom here. And then it pops up in a few places and stays on the atmosphere, next to the atmosphere. There's the structure related to the Gulf Stream. It's not quite the Gulf Stream, but there's this river of surface water that, because it's thinner, goes much faster. Okay? And as it zooms along, CO2 from the air wants to dissolve into the water. All right? Because the water contains dissolved CO2. And if you remember anything from high school chemistry or from college chemistry, then you'll remember that gases, when they diffuse into subjects, want to reach an equilibrium. All right? The water wants to hold a certain amount of CO2. And if the CO2 concentration that it holds is too much for the air, higher than what should be there, it escapes, net escape from the water and goes into the air. And if the reverse is true, it goes into the water. So the two reach an equilibrium. And the more the CO2 is in the air, the more will dissolve into the water. And so when this water comes up and goes along here, it exchanges CO2 rapidly with the air and comes into equilibrium. And because that air is recent and has high CO2 in it, it absorbs CO2 because, see, it's been crawling on the bottom here for 1,000 years. It last saw the atmosphere 1,000 years ago before humanity invented fossil fuels. And so when it comes up, it's CO2 starved. It sees this CO2-rich atmosphere and it takes up CO2 as it moves along here. And that will continue happening for like 1,000 years. As long as the concentration of CO2 along this red journey is higher than the CO2 concentration when the water went underground, right, went into the deep, which was 1,000 years ago. Which means as long as the atmospheric CO2 concentration is higher than it was in the pre-industrial, it'll keep happening. That sink will persist. So I have like a little, like really lame cartoon I've made up. Okay? It's like super lame. But I did it anyway. And this has the atmospheric concentration. 280 is tan, 400 is sort of lighter, regular brown, and 450 is dark brown. And these are the corresponding CO2s in the oceans. Light for 280, medium for 400, and heavy for dark blue. And so here's a situation in which there's a 450 ppm atmosphere, and we've just snapped to it. We've taken a 280 ppm world, and we've just like gone boom and dumped 450 ppm into the atmosphere. And so the shallow ocean is upwelling here. Here's the Red River, and then it goes down again and stays in the deep for a long time. The shallow ocean is got a lot of CO2 in it because it's taking all this up from the atmosphere, and then it's going down here and it's spreading across through time. Just keep waiting, see it does that. You get it? All right. Then all of a sudden, if we now jump instantaneously to 400 ppm, we're going to drop the atmospheric CO2 concentration. And what happens? Now, This is lighter blue because it's in equilibrium with a lower CO2 atmosphere. But this lighter blue now starts filling up the ocean, right? And it looks like that, and the ocean is still gaining CO2, just not at the same rate that it was before. You see that? Because the ocean is getting darker and darker. And so that's why the sink persists. Just that. And then there's a couple of slides here I'm not going to hold you responsible for that show that the way that forests work is exactly the same thing, except not quite as dramatic. And it's because the centers of trees were built a long time ago when the atmospheric CO2 concentration was lower. And as it were, they have to fill up with CO2. Okay? So the ground, the forest's carbon today represents like 100-year average of past atmospheric CO2s. And that 100-year, yeah.
I was wondering, with the ocean filling up with more CO2, does it change the chemistry of the ocean?
Yeah, it does. Yeah, so the atmosphere, so the chemistry is this ocean acidification problem, right? And so it makes the oceans more acid. And it creates problems for corals and other organisms that have calcium carbonate shells. So yeah, it's a problem. Yeah. Okay, so the bottom line here is that it is possible to reduce atmospheric CO2 even without negative emissions technologies. And in other words, not just emissions, but the absolute magnitude by getting emissions low enough that the sinks dominate and pull the CO2 out of the atmosphere. And in RCP 2.6, it's really the sinks that are doing the concentration reduction. And the negative emissions are just helping humanity get fossil fuel emissions positive but lower for the rest of the century. All right? You get that? So think about it as just another way to mitigate. All right? Just a way to reduce emissions. Think of it as offsets. And so there's a bunch of words here you can put. All right. So I want to talk about a bunch of the different options. What are the technologies themselves? The first one here, I'll talk about these options first. So the first and simplest way to do it is to reforest or afforest land. Reforestation is to take land that used to be forested, that is now agricultural or it's cropland or pasture land, and you plant trees on it. And then those trees take up CO2 and convert it into wood, and eventually there's a forest. The trees keep dying, but new ones are born. And the forest itself goes from this much carbon above and below ground to this much carbon above and below ground in a hectare. So on average, over, if it's tropical lands, over a period of 100 years or more, it'll pull down 900 tons of CO2 per hectare. It's a lot, right? It's super effective. And this is interesting. And it's something that, remember, we heard a lot about in Kenya as a political movement. But there are concerns about doing this at scale. Could we really do 10 gigatons a year of this? The concerns are, remember I said that land has to be from somewhere, right? If it's reforested, it's cropland or pasture that used to be forest. If it's afforested, it's cropland or pasture that was never forest. You're going to plant trees on it anyway. Either way, it's coming out of food production. And that food production might be marginal land, but one person's piece of marginal land is typically a poor person's essential means of livelihood. All right? So doing 10 gigatons of this is really hard. I mean, you have to pull a lot of land out of food production, and then you get into the Arab Spring and the Syrian Civil War. There's all this terrible stuff happens. There are also issues of permanence. Who's going to say somebody's going to come cut down that forest later and convert it back into cropland? It has to stay forest forever. And then there are biophysical impacts. It turns out if you do this in the tropics, it's actually true that you help cool the planet. If you do it in the boreal, if you do this like across Canada and Russia, it actually turns out to warm the planet. And the reason is that the trees you plant are so much darker than the snow that was on the ground that the change in the albedo causes the surface to absorb more sunlight and actually heats things up. So it has the reverse effect. You can really only do this forestry in the tropics, which is where we've got the food concerns. All right, so, but there are some co-benefits. And it's why the Nature Conservancy, the same group, has a huge amount of this. They're saying, you know, we could do 3 gigatons of CO2 per year of this. And if you figure out how much land that's going to require, it's a lot. It's hundreds of millions of hectares out of a total of like 1,500 million hectares. So it's a large fraction of total food production. TNC wants to do this because they want to preserve land. But this option, I think, is really strongly limited by the other Nexus problems. All right? Not by the carbon problem, but by the other Nexus problems, the food and the biodiversity problems in particular. So this is the problem. All right? And so they say there's a lot of this that we can do, up to 3 gigatons of CO2 per year, as big as avoiding all tropical deforestation. But if you did that, that land's coming from something else that humanity values. There is one way of doing this that a bunch of us dreamed up recently, and it's just, I like it because it runs against ecological sensibility. So imagine that you were to stop recycling. You decided recycling is a terrible thing to do, and people who recycle are losers and they're bad people. And why would that be? It would be because what you're supposed to do is you're supposed to use as many wood products as you possibly can. Because when you recycle them, you put them in a separate bin. And instead of going to the town's municipal landfill, it goes to a special landfill, which turns out to be cheaper to make. And it's a landfill you should think of as a wood tomb, okay? It's dry on the inside. This isn't one. There is none. There's this guy. So this isn't from, a bunch of us dreamed up the idea, but this is the guy who really knows about it. Morton Barlas is the world's greatest theoretician of dumps. He knows more about dumps. He's the head of the Department of Civil Engineering at NC State. And he knows like everything about dumps. And he can do math about dumps, and the EPA uses only him. Everybody who wants to know about dumps goes to Morton. He's a really nice guy, and he is so excited by dumps. Okay? And Morton says, yeah, I can make you a wood tomb. It's cheap to make you a wood tomb. $7 a ton, $10 a ton, something like that. Just change the place the truck goes, put it in a tomb, and it stays in the ground forever. And that means that creates a river that goes into the trees, goes into the wood products, goes into the dump, and you can keep it running as long as you're willing to make dumps, wood tomb dumps. And you can actually get big numbers from this. It's actually interesting. And it doesn't create the same kind of external difficulties with the other Nexus problems that reforestation does. I actually think this is an interesting idea, but it would cause us to think that recycling is bad. Because recycling can end up returning some of the CO2 to the atmosphere. What you want to do is keep harvesting the wood and keep stuffing it below ground. After we've used it up, start a throwaway society, nothing built for last, all that kind of stuff. Throw away all the packaging all the time, have giant mounds of trash out of the curb, all that stuff. All right. So, afforestation, reforestation, and tree planting that isn't going to wood tombs is inexpensive and ready to deploy, but I think it's probably limited to 1 to 3 gigatons of CO2 globally, and probably less than that, probably less than 1. There's also this variant that I talked about, which is biomass energy with carbon capture and storage. It's expensive. That's where you're, burning the trees and then you're capturing the CO2 and putting it below ground. Bottom line is it's expensive, and it has the same problems as doing reforestation, because you actually have to create the biofuel to burn in the plant. So that's also limited because of the other Nexus problems. All right? This is where the IPCC gets it wrong, because they don't sort of study the problem as an intersection of 4 problems. They study the climate problem in its isolation, right? Okay, so where am I? Okay, so soil sequestration, sort of the same thing. You do like no-till farming and put a cover crop on there to manage the land so that you increase the amount of soil carbon. Nice thing about doing this is that when you increase the amount of soil carbon, the yield per hectare goes up. The farm income typically stops oscillating so much, so it stabilizes farm incomes, increases the mean, decreases the variance, increases water holding capacity. It usually improves nitrogen retention so that you need to put less fertilizer on and less of it runs off. So it's like win, 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 win here. And a lot of this is actually done now, but it's still only 20% of land that is done this way. And one of the big reasons is that the equipment costs a lot of money. They have to have a fancy pants drill to drill the seeds into the soil. And that costs like $1 bajillion. And so in the US, we're actually a bunch of us trying to work on a farm bill right now to get farmers paid to do this because you can store a lot of CO2 that way. The concerns, there are none, and there's just tons of co-benefits, right? So this is a win-win that you can rebuild the greatness of America's soils and still store carbon. It looks like there's maybe 1.5 gigatons of CO2 annually that could be done at less than $20 a ton, but many of these hectares are at negative cost, right? So you actually save money by doing this if you can afford the equipment and pay off the loan. So I think there's some real potential here. This could, in the US, for instance, replace the clean power plant that Trump and Pruitt aren't supporting. This is just we know that this works because of hundreds of long-term experiments. And this is tons of carbon per hectare, and this is carbon storage per year. And if anybody knows about this sort of thing, if you're an engineer, this is a differential equation, which says that carbon is going to increase in the soil. And it increases for typically 50 to 100 years. So you do this, you start this stuff, your land improves for 50 to 100 years, you just keep storing carbon. And we have huge experiments to do this. And this TNC report, the whole middle of it is about that. So this is expensive and ready to deploy on croplands. It's inexpensive and ready to deploy on croplands. Inexpensive and ready to deploy only in some cases on grazing land. If you look online, you'll see a lot of TED Talks with people aimed at rich people that are trying to get them to manage their grazing lands, particularly in the American West, to store carbon. A lot of the things they're saying haven't been shown to work. There's a huge amount of experimentation on cropland soils, much less on grazing lands. We need more. Simple to do, but we only know how it works on some grazing lands. The more arid the grazing land, the less we know how well it works generally. All right. So there's room here for some science, and cheap, easy science, right? Science that you just sort of do when you find out the answer. I think there's 1 to 3 gigatons of CO2 globally. All of it at less than $50 a ton. Most negative costs. This is a big deal, right? We ought to do this as a species. This will be useful. Direct air capture. Direct air capture is cool. This is one of those machines that I was talking about. They got them in a stack here. This stack is in Iceland, and it's taking the CO2 and sticking it in a basalt formation where it's turning into stone. And this group in Iceland is doing this to offset the power plant's fossil emissions. So this is a zero emissions power plant because for each gallon of fuel they're burning, they're putting in 10 kilograms of CO2 and they've got a negative net emission. I actually think we may do this for a long time as a species if we end up solving the carbon problem. And the reason is aviation. Turns out it's really hard to run a zero carbon airplane. We can run a zero carbon car and truck really easily because we can run it off of renewable and gas with CCS electricity, and it's an electric car and electric truck. You can make electric airplanes, you can buy them now. They're all the rage, but they don't go very far, okay? You go like 20 miles and that's it, right, or 100 miles an hour. And so if you need to fly, and I want to fly places. I mean, I like going to places, you do too. And how are we going to keep doing that? And the answer is if we can get the cost of this down to $1 a gallon, that is $100 a ton. Right? Get this down to $1 a gallon, then aviation gas costs about $2 to produce. And if you add $1 to it, have $3 a gallon for aviation gas. And if you compare that to, for instance, cellulosic biofuels, you'll beat them on price. And there's no externalities for this, right? This is just equal direct emissions, but this one includes to do a lot of biofuels, you gotta convert farmland to making gasoline, right? That's not so good. So I actually think there's a big future for this, and if you're looking for a startup to do, there's like running room like crazy to do this, right? There's so many different, it's just one of these things that's much more like cooking than it is like a fundamental invention. There's the search for some materials. Edisonians search for like perfect absorb it. And if you discover it, you've all of a sudden got this gigantic winner, and there's a huge array of things that one could do. So if you're chemically minded, this is a good area. Okay, so the punchline I want to make is that we should deploy NETs, that is negative emissions technologies, that are ready now and accelerate research on the rest. There is the opportunity, these will play, in my view, a role in the future. But this idea that we're going to be doing 10 gigatons per year of it by 2050 and 20 gigatons per year by the end of the century, it's not going to happen if we use the tried and true methods of reforestation and afforestation and soil management. We'll get a fraction of that, maybe half. And if we go beyond that, we're going to start causing real trouble with our food system, or we're going to be converting land from tropical rainforest into biofuels plantations and have big effects on biodiversity. To actually get to those bigger numbers, we actually have to invent something cool. All right, and so I don't believe these are CP 2.6s, but I also believe that, as I showed you last time, that humanity has invented a mix that allows essentially zero emissions right now. And so I think we can get to the low net number without deploying gigatons, because I think the world has changed since the IPCC with the drop in costs, particularly in wind and solar. And once we get positive emissions down low enough, the atmosphere starts pulling the CO2 out of the sinks on the oceans and on the biosphere start pulling CO2 out of the atmosphere, and we get this decline back to really safe levels. So a way to do this without the massive and if you want, you can click your clicker as you go out the door here, okay? So thanks a lot. One more class.